three charges Q, minus Q and 2Q are placed at the corners of an equilateral triangle. So let's draw an equilateral triangle over here. Let's say this is our equilateral triangle with charges Q, minus Q and 2Q over here, and having a side length of A. So each side of this equilateral triangle is A over here. The net force acting on the charge minus Q, you have to find the charge on net force acting on minus Q. So let me just keep it here, minus Q over here. Okay, we have to calculate. So we know that if we call it as A, let's call it as B, let's call it as C. The force between A and C, that A and B, sorry, that will be attractive. So it will be along the line joining the two charges. So let me call it as FBA, force on B due to A. Force on B due to C, that will be acting in this direction. So force on B due to C, and the angle between them is 60 degree, right? So let's write here theta is 60 degree. If theta is 60 degree, then cos 60 over here, that will be nothing but half. Great. So here our resultant R, that will be equals to root under, we know that FBA square plus FBC square plus 2 times FBA BC into half. Cos 60 is half. So let's figure out what is the value of FBA and FBC. So let me just write it over here. FBA, that will be by Coulomb's law, K Q1, we will not take the negative sign, Q2, so KQ square by separation A square. Similarly, force on B due to C, that will be equals to K Q and into 2Q, so that will be 2Q square upon A square. So let's substitute these values over here. That will give us KQ square by A square whole square. FBC square, that will be 4 times KQ square by A square whole square, and plus FBA into FBC, that will be 2 times KQ square by A square whole square. Yeah. Now let's take common here. This will give us KQ square by A square whole square. Taking common, we left with 1 plus 4 plus 2. So this will give us 4 plus 2, 6 plus 1, 7. So this will be root 7 KQ square by A square. So correct answer is option C. I'll move to the next one. Two charges Q1 and Q2 are separated by a distance d. So let me just write here that let's say this is our Q1 and let's say this is our Q2, and both are separated by a distance capital D. If both Q1 and D are doubled, so even Q1 is doubled and D is doubled, the force will become how much? So let's say what is the force initially? The force F will be K Q1 Q2 whole divided by D square. Now when Q1 is doubled, the new Q1 will be Q1 dash, that will be equal to twice of Q1, and new distance, new separation D dash is twice of D. So the new force will be F dash, that will be equal to K new charge on the Q1 into Q2 is still same whole divided by D dash whole square. Let's substitute the values. So this will be K into 2Q1 into Q2 whole divided by twice of D whole square. So that will give us here as 2 times K Q1 Q2 whole divided by 4D square. Now K Q1 Q2 over D square, that's nothing but this part over here, that is nothing but force, the previous force. So it will be 2 by 4, that is 1 by 2 of F, that is F dash. So the correct answer is, it is halved. Understood? Let's see, the next one says unit of permittivity. Unit of permittivity is our Coulomb square per Newton meter square. That's the correct answer. So this is option D. Let's move to the next one. Let's see. So question here says dimensions of epsilon naught. So first of all, the unit of time for that, let's first write Coulomb's law. F equal to 1 by 4 pi epsilon naught Q1 Q2 whole divided by R square. So epsilon naught, that will be nothing but Q1 Q2 whole divided by 4 pi epsilon naught FR square. And if we write the units for Coulomb square whole divided by Newton meter square, that will be the units. Now let's write the dimensions. So first oh sorry, yeah, my mistake. Okay, so now this will be Coulomb square per Newton meter square, and here the Coulomb has a dimensions of AT, where A stands for ampere, T for time. From 10th standard, I is equals to Q by T. So Q is nothing but I into T. So current has a unit of ampere and time has second. So dimensions is AT, and N Newton is M1 L1 T minus 2 meter square, that's nothing but L square. So when you take it on the top, this will become M minus 1 L minus 3, and A is as it is, and T power plus 2, and A square, no, T is plus 3, I think minus 2 goes up, it will be minus, so it will be square over here. I have done a small mistake, yes, so it will be A square, and T will be T to power 4, and this minus T square, and this T to power minus 4 it will be. So minus, it will go up and it will be plus, so that will be yes. So that will be option B is the correct one. Yeah. So maximum they can give you up till 4 charges, right? So question over here says 4 charges Q, Q, Q and minus Q are placed at the corners of a square. So let me just draw a square over here. Let's say this is our square and this is our Q, 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 and you have to put it in the same order. So it will be minus Q over here, right? Okay, side length of each of this is A, right? The net force acting on minus Q. Now minus Q is attracted along this direction by the first charge. So let me call it as F1. It is attracted towards the second charge. Let's call it as F2 along this direction, and F3 along this direction. Correct? Now F1 and F3 both are at 90 degrees. So let's first find F1 magnitude. So F1 magnitude is nothing but K Q square by A square. Alright. And F2, that will be K Q square by A square. Both are equal. F3, not F2. Yes, F3 is K Q square by A square. Now the resultant of any two vectors which are perpendicular to each other, you can directly write it as A square plus B square. You can put it as A square plus B square plus 2AB cos theta, but theta is 90 over there. So cos 90 is 0. So here if A square and B square both are same, then we can straight away write it as A square plus A square, and that is nothing but twice of A square, which is root 2A. So adding F1 and F3, they are both same. So resultant of F1 and F3, that will be simply R will be equal to root 2. You can write any value because both are equal, K Q square by A square. And where will be the direction? From parallelogram law of vector addition, if both are equal vectors, that will be inclined equally at 45 degree. So this is our R. Now as we can see that R and F2 are along the same direction. So we can directly add them because the theta is 0 degree between them. So F2 is nothing but K, first charge is Q, second charge is minus Q, so K Q square whole divided by the separation between this minus Q and that minus Q. Now there you need simple Pythagoras theorem, so you can write it as root 2A. That's the separation between minus Q and that plus Q. So this whole square, which will give us K Q square over 2A square, right? So this is F2. So net force acting on minus Q charge will be F2 plus R, and F2 is nothing but K Q square by 2A square and plus K root 2 square by A. Now let's take K Q square by A square common, and we left with over here as into 1 by 2 plus root 2, and that's nothing but option A. Understood? Okay, so in the last lecture we defined Coulomb's law. Okay, now in Coulomb's law we learnt that how we find the force between the two charges. Okay, let it be positive two charges, negative two charges. Okay, and this was our Coulomb's law in the previous lecture. The force was proportional to the product of the two charges and inversely proportional to the square of the distance between them. Okay. Now then we require one more concept to define force, and that concept is concept of electric field. So let me just write here electric field. Let me zoom it a little bit. Okay. So here it is electric field. Our next topic is electric field. Sir, what do you mean by electric field? Electric field is a region around any charge. So let's say if there is a charge, positive charge, you can think of negative charge also. There is a region around this charge. Around every charge there is a region, and in this region, if you take a negative or another positive charge or any charge inside this region, it will experience a force. If you keep it outside this region, there will be no force. I think you must have done this with the magnets also. If you take a magnet and this is another magnet, north attracts south, but up till a region. Like if you keep the magnet in one room, another magnet in any other room, not necessarily they will attract depending on that field. But if you keep them close by, they will attract, right? So electric field is a necessity to define force. It is a necessity to define Coulomb's force. So let's define electric field. What is electric field? It can be defined as the force that a unit positive charge would experience if placed at that point. Which means if you place a small positive charge at any point in the region of the source charge, we call this charge as source charge, whose electric field we are looking for. If you place this small test charge in the region around this positive charge, it will experience a force. Sir, why you are talking about this test charge being small? This should be small so that it should not affect the field or the position of the source charge. If by any chance if I place this small q over here, it should not change the position of the source charge. Okay. So positive charge plus q, the field at any point r distance away. So let me just draw it over, not here. Let me just draw it that side, this small q. So that let's say we are placing it over here, and this is our source charge, and let's say this is the region, this is the point at which we are finding the electric field. So according to Coulomb's law, the force acting between both will be equals to k q over r square, where k is nothing but 1 by 4 pi epsilon naught, right? Now if I take the small q on the left hand side, F by q, this will give us a quantity, and that quantity is known as the electric field. And F by q is nothing but the electric field at that point, due to whom? Due to the source charge. So you can see on the right hand side, capital Q is the only parameter on which and the position at which it is dependent. Both are inverse square laws, means R, it depends on R. If you increase, electric field will decrease gradually. Clear? So this is our electric field. Any doubt? You can copy if you want to. Let's move to the properties of electric field. So let me write some properties of electric field, then we will see how we can represent them geometrically. Okay. So let's write here properties of electric field. Properties of electric field. Very important for problems. So let's see the first property. If Q is unity, if the charge, small charge Q is unity, let's go back to our expression. Small q is unity, which means the electric field is equal to the force, right? Because if Q becomes 1 over here in this expression, then this expression converts into electric field and F will be equal to E, right? So if Q is unity, the electric field due to charge Q is numerically is numerically equal to force exerted by it. This is the first point. Let's see the second point. The second point over here is the electric field E. The electric field E due to Q, due to capital Q, is independent of test charge. That we have seen in the expression as well. Independent of test charge small q. Sir, how? Simply we know the expression. Our expression of E is nothing but K capital Q by R square. It doesn't contain any small q. So let's see the next point. This is the second point. Let's see the third one, and very important here. Important point. For a positive charge, the electric field will be directed radially outward from the charge, away from the charge. We will see that in field lines. For the time being, we just take that it is radially outward for a positive charge. What about negative charge? For a negative charge, the electric field will be directed radially inward towards the charge. These are just conventions. These are called properties of electric field. Yeah. Let's see now, how do we represent an electric field? So, electric field is represented by, the geometrical representation of electric field is known as electric field lines. Electric field lines. Sir, what are electric field lines? They are just a geometrical representation of electric field. So, these are geometrical representation of electric field. So, you represent it. Do electric field is a real thing? Yes, electric field is a real thing. Is electric field lines a real thing? No, they are just representation. So, how do we represent, sir? If you take a positive charge, you can represent it like field lines like this. They are radially away for a positive charge. We will see problems based on these field lines. They will be used in the applications in the upcoming part. For a negative charge, they are radially inward towards the negative charge. But if there is a positive and a negative charge, and we will see such a system, we call it as a dipole. We will talk about electric dipole after a few minutes. So, if there is a positive and there is a negative charge, the field lines will go from positive to negative. So, they are going like this, they are going like this away from this, and here it is coming inside towards the negative charge. So, this is the way we represent electric field lines for a electric dipole. Exactly, quite similar but not exact. That we will see in the magnetic field lines, because that is the differentiator. Okay, there will be a different thing which will be like quite different in case of a magnet. Done? Yeah. Now the most important part for CBSE, they often ask this question, that is properties of electric field lines. That's very important. Properties of electric field lines. Electric field lines. Let's see what are the different properties of electric field lines. So the first property that we know, that is field lines. Okay. Start from a positive charge, and ends at if there is a negative charge. If there is no negative charge, they will go to infinity. Okay. So let me just write this also. If there is a single charge, they may start, in case of a negative charge, they might come from the infinity. So they may start from infinity, and for a positive charge, they may go and end at infinity. So that is the situation for first property of field line. Let's see the second part. If let's say there is no charge in between, there was some charge which is placed at my home right now, let's say. Outside my home, there is no other charge. In such a place where there is no charge, then these field lines which were coming out because of some particular charge, so in a region free from charge, electric field lines can be taken to be continuous curves. They are continuous without I'll explain, without any breaks. So what can't be possible? If this is a positive charge, the field line which is going from here can be like this, can be like this, but it can't be like this. You can't have breaks. It can't be like this. This is not possible. Your field line cannot be like this. Though they are going away from the charge, but still there are breaks in between. So breaks are not possible if there is no other charge. If there is another charge, that we have seen in a dipole, that we will see later on again. So this is another property of electric field line. Let's see the next one. Next one says, two field lines can never cross each other. Can never cross each other. Now this is crucial one. This is the mostly asked property of electric field lines. Two field lines can never cross each other. Now question is why? They ask this question in 1 mark also, separately, not asking in properties of field lines, but they can ask you in 1 mark question that why two field lines can never cross each other? Because, this is the reason, because if they did, the field at the point of intersection will not have a unique direction. Now, so what does it mean? It simply means, let's say there was a field line which was coming from any positive charge or a negative charge, or it is going outward, let's say, like this. Another field line, let's say this is the second field line which is going like this. Now I am assuming that these two cross each other. Now if they are crossing each other, they are crossing it at any point P. Now if I release a charge at this point. Now according to Coulomb's law, it will experience a force. So this electron will go along this direction. And if I release an electron over here, it will go along the field line like this direction. But if the same electron, if it reaches at point P, it gets confused. Like it should go along the pink one or the red one. So this confusion arises because of the intersection. Because point P doesn't have a unique direction. Every point has a unique direction. If a train is moving on the red path, it knows that it will go along this direction. If I release it at any point, I know that it will go along this direction. No other point. And if there is a train which is moving on the pink path, we know that it will move along this direction. But if the train reaches point P, you can't say that it will go along the pink or along the red until you know the past, right? So P is not having a unique direction. Hence, no two field lines can cross each other. So this is a very important and often asked property of field line. Finally, the last one. And the last one says field lines do not form any closed loop. Now, sir, what do you mean by closed loops? Simply, a field line can never look like this, that it went from here and it came back here. No loop like this. Or it is like one field line is going like this, another one is going like this, and one field line is going like this. No, this is not possible. First one is possible, second one is possible, third one is not possible. So such fields we can't have. So field lines can never have closed loops. These were our properties of electric field lines. I'll move to the next topic. Let's see our next topic. Our next topic is an electric dipole. So let me just write here electric dipole. Sir, what is an electric dipole? An electric dipole, it's a pair. It's a pair of equal and opposite charges Q and minus Q separated by a distance 2a. Okay. So before I explain, just focus on this part, that we are dealing with two charges which are equal and opposite. So sir, can it be Q, 2Q and minus 2Q? Yes, of course, this is an electric dipole. Sir, can it be 5Q and minus 2Q? No, it can't be an electric dipole. Sir, equal and opposite. So sir, can it be 5Q and 5Q? No, still it is not opposite. Be very careful. It should be equal and opposite. So these are the conditions. Can it be minus 2Q and minus 2Q? No, it's still not equal and opposite. So an electric dipole, the very basic definition of electric dipole is the charges should be equal and opposite, and they are separated by a certain distance. So sir, if they are separated by a certain distance, why you are taking that distance as 2a? We are taking this distance as 2a because when we will derive some expressions, we will require the separation from the midpoint of this dipole. So you can also call it as L, that's also fine, 2a or L, that's okay. But we usually take it as 2a because this 2a, when you take it from midpoint, this gap becomes a and this gap becomes a, instead of writing a by 2, a by 2. Exactly. So instead of making L by 2, L by 2 or a by 2, a by 2, we just take the whole thing as 2a. So that when you want to take the separation from midpoint, exactly, it will be that thing. But because this is done in class, okay, like 2a, most of the students, they make it wrong. Like if they are given the separation between the two charges as 10 centimeter and define the dipole moment, we will talk about dipole moment. There they will directly multiply 10 with 2. I don't know why. So be very careful. 2a is the separation between the two charges. So dipole moment, let's talk about dipole moment. So dipole moment over here, we define a quantity. We will understand the core concept of that later on. Okay. So right now dipole moment, we can define it as a vector quantity P, and that can be defined as, that is dependent on the configuration or geometrical configuration of this dipole, that is 2a, the separation, into q. Now 2a is the total separation. Be very careful. If it is 10 centimeter, you have to take here 10 centimeter straight away. No need of multiplying it with 2 or no need of dividing it by 2. Straight away 2a, 10. Okay. Q is charge. Now we take the magnitude. We don't take the direction. Why? Because direction is always from negative to positive charge. That's a dipole. Okay. Now if you look at the unit of dipole moment, that will be nothing but unit of dipole, this charge, Coulomb, and unit of distance is meter. So be very careful. It looks like centimeter, but you have to keep the capital C. Okay. So this is our dipole and dipole moment.